sir. Thank you. Dr. P.P. Murthy, sir. He has given me opportunity to give opportunity to introduce Veeramani sir for this session. Thank you, Murthy sir. So now in second session we have again Professor Veeramani sir, and his lecture topic is the role of multi-valued fixed point theorems in the study of existence of Nash equilibrium points. So now I request to Professor Veeramani sir to continue this session. Thank you so much.
Thank you again. I think some pen, marker, and oh here, yeah. No, it's okay. Yeah, it's so good. Okay. So before starting, feel free to ask whatever doubt you have. Otherwise, as I told, if you are not asking, then I will have to ask. So better you ask. Anyone? Okay. We'll go back even to the very first day. Again, I will ask some questions. Okay. What we have seen that even more generally for this continuation of previous lecture, and then we will concentrate something remaining from whatever related to existence of Nash equilibrium point. Yesterday we saw only for two players. More generally any number of players, but we will restrict to infinite number of players. Okay. But before that, some questions for A, comma B belongs to R, A strictly less than B. We know that F from closed interval A comma B to the same set, self map, continuous, imply, what is the conclusion? There exists, it has a fixed point. What is the property we are using? It is an interval, correct? What is the relation between interval and connected set in R? Any relation between connected set and intervals? In our case, we are in R. What is the relation? Both are intervals are connected sets are interval. Interval are the only connected sets in R. So this we can prove using again LUB axiom, or so then this imply there exists X belongs to the domain such that Fx equal to X. This we have seen. Suppose now we are moving from in place of closed interval A comma B. What is closed interval? What are the, see, if you want to go from dimension 1 here, R2, next, okay, we will see what will happen to even R2. Closed interval A comma B is a closed, bounded and connected. In fact, we did not talk about convex at this stage. In fact, we at the here this closed interval A comma B is closed A comma B, closed, non-empty is always there. Closed, this I am writing for bounded and connected. Connected subset of set of real numbers. So what will be the natural thing when you go to R2? So in place of closed interval A comma B, now take capital A or K, whatever may be. Capital K, non-empty subset of R2. What we expect naturally. From that, we want to formulate a statement, we were trying to generalize, whether we can extend the similar result to R2. Then we can do R2, then finite dimensional, then infinite dimensional, like that. So what will be the state condition on K we expect using our knowledge of closed interval A comma B? We know A comma B is closed and bounded, okay? Closed and bounded, even right now we don't bother about compact. We are finite dimensional, every closed and bounded set is compact. Even some not familiar at the lower level, we can just say closed and bounded in R. R2 also, and it is connected. So what you expect that K should be of what type of set? K is a non-empty, closed, bounded and connected. So that is quite natural. So suppose K, K closed, bounded, connected subset of R, and F from K to K continuous. Then question, whether we are forming the statement in a natural way, but the answer, conclusion, hypothesis we have made the statement. Then we are asking the question whether there exists, what is our question? Whether there exists, whether it has a fixed point. That means whether there exists x in the domain K such that fx equal to x. Question is clear? Now answer. You tell the answer. Answer is simple. Whether there exists x in K such that fx equal to x. We are assuming closed, bounded, connected. Like we are translating the domain closed interval A comma B in R is closed, bounded, connected. What will happen if you assume the same conditions for a subset of R2 and the same condition F from the map is continuous? Can you expect a point x in K say that fx equal to x? Pardon? Okay, if not the answer, what you feel at least? Anyone? Some of your experts? Very good. No. Is a research scholar in fixed point theory, no? So you should know. Okay. Okay. He is saying answer is no. So then you have to prove it. Prove mean? What do you mean by that? Means that what we call it, the result is not true mean what we will do? Give a example. At least one example we will have to give. Give an example. Our set is closed, bounded, connected and a map F from K to K continuous, but there exists no x in the domain such that fx equal to x. I think he knows the answer. Correct? Example? Okay, what if anyone else? Yes, already given the hint, it is not true. Yes, it is correct. What natural example one can think of? We have to go to R2, not R. Pardon? What is the original statement of Prover? If you see, Prover would have also thought, okay, we do not know, but it is one of the natural way. What is the statement of Prover's theorem?
Closed and continuous map has a fixed point.
Closed, bounded,
Compact.
no, closed bounded means compact in a R2 or finite dimensional. It is compact. Other additional condition? Convex, not connected. So, R2 in R2. What is the relation between convex set and connected set? Which implies which? Every connected here in R there is no difference between connected set and convex set. That's why we did not even introduce the term convex set. We were not knowing. So then we would not say that K is closed bounded convex. We were not even knowing at the initial. Suppose we are teaching for a beginners before introducing even convex set. Teach this using intermediate value theorem. Then what we will do? Yeah, but why convex is more important there? Of course, the proof is, that's what as they say topological idea, but in example is simple. Okay. See, in fact, Prover proved first for unit ball in R2. What is the unit ball mean? For x in R2, R2 mean x equal to order pair x1 comma x2. What is the length of the vector? We define positive root of x1 square plus x2 square. That is our norm. Length, norm mean distance between the point 0 vector and the x. That is what norm of x, length of the vector. Then what will and the domain, what is the unit ball? Unit ball, say capital U or closed unit ball, set of all x in R2, say that norm of x is less than norm in, that is this is equal to x squared, that is if and only if x squared plus y squared equal to 1. Equal to 1, yeah, here we have less than or equal to, so that's why we get a ball, circle, unit sphere equal to 1 mean here, suppose a point here, anywhere. Don't worry about the notation, here also x understood, variable they are. Okay. So here means norm x is 1. Suppose some y interior, then norm y is less than 1. This set is convex. If you take any 2 points, the line segment joining, those 2 points are there. The unit ball is convex. So every convex set is in fact pathwise connected. I mean just you can start with any xy. So like that, if we start with xy, we can define f from closed 0 1 to r as f of t 1 minus t time x plus t time y, meaning at time 0 you are at t0, you are at x, t1 mean at y. So this is a continuous function, f is a continuous function from closed interval 0 1 to the unit ball, such that f at 0 is x, f at 1 equal to y. This is true. I mean the function depends upon xy. We are not written f suffix xy or like that. Another xy mean another function, not the same function. Okay. I mean domain is closed interval 0 1, codomain is the unit ball, but we want that at 0, that's at that time 0 we are here. Keep walking, after 1 hour we will reach the destination y. So it is pathwise connected, imply it is connected. Okay. From here can you think of a subset which is connected but not convex from the unit ball. You have unit ball. See, this is a nice unit ball. From here you think of a subset. Very good. That's why I draw only circle. Okay. Very good. That is nice. See, we call this set as whatever it only set of all x belongs to our U. Now only the boundary. This. If you take any 2 point, we cannot join by a line segment. Here 1 point, here means the line segment will not be there. It is not a convex set. Is it a connected set? Yes. Continuous. Why it is connected? Continuous image of a connected set is connected. We can prove. Okay. These are all simple. Okay. You know that this is connected, but not convex. Can you define a function from S to our A or K we have taken? Can we take this? Define f from S to S as f of x equal to, in fact what we call it, fx equal to, even define x is on the boundary, the image should be also on the boundary. So one natural way is using x which you can, which point will give you x. Using x, you have to get another element, again it should be in S, that means norm should be 1. Pardon? Cos x sin x. Correct? Cos x, yeah, what he is saying is cos x. What is x? X belongs to where? X belongs to R2. So you introduce what is cos of some element order per x1, x2. Okay. Simple thing is, I mean, if it is order per x1, x2, then you can change it to that way. So, okay, again to think that what is the natural more, I mean, as he say, we can go for cos x1 plus fx equal to now you can tell minus, which it depends upon x. If using x only you have to define now. So fx equal to minus x. See, now what is norm fx? Equal to norm of minus x equal to norm x. In fact, it is something, what type of map? It is continuous, you can check easily. In fact, f from R to R, norm of fx minus fy equal to, norm in, we have defined that positive root of x equal to order per x1, x2 mean norm x is root of x1 square plus x2 square, Euclidean norm. So fx equal to norm x minus x, then minus of fy minus y, this is nothing but norm of minus x plus y, that is the same as norm of x minus y. In fact, this is a isometry. Such case, that is, we have norm of fx, distance between, this what we call it, distance between fx and fy equal to distance between x comma y. Forget about continuity, it is very strong, it is uniformly continuous isometry. It's a very strong condition, still it doesn't have, can there exist? What will happen? Suppose there exists x in our domain such that fx equal to x, then that implies fx is minus x equal to x, that implies 2x equal to 0, that means x. we are a vector space, X is a vector. So that means that is possible only when X is 0, but our X is where? On norm of, what is norm of 0? 0. But here, so then it will have, our started X is in the unit sphere, norm X equal to 1. So you will get a contradiction. So there cannot exist not only any continuous function, even in isometry. Even if it is an isometry, if we remove, now we are going to discuss about non-expansive map also. What is non-expansive? Professor Perande has discussed many times. Our main interest is, domain is, our domain closed, bounded, convex. T, F or T map from that set K to K. So that norm of Tx minus Ty, that means distance between Tx and Ty less than or equal to distance between xy. For all xy in K, then such a map is called non-expansive. Whether this map is non-expansive? Yeah. 2 less than or equal to 2 is true? True. 2 less than or equal to 3? True, okay. Okay, these are all trivial, we know, just, because some are young students are also there, just, okay. Norm of 2 equal to 2 imply 2 less than or equal to 2. Less than or equal to means a relation. Either x less than or equal to y mean either x is less than y or equal, any one. So we know this. So not only, even if the map is non-expansive or more stronger is isometry, if the domain is nice compact set and connected set, still it need not have a fixed point. So the convexity we cannot get away from the assumption. Convexity assumption is very important. Of course, the proof is, those who are interested, you can, even Mungers you can see the proof, and many other books you can see. Topology by Mungers. Okay, this then and that. Again, morning Professor Murthy pointed out about R is complete. We proved it in the first day or the first lecture. Set of real number is complete. We completed the proof. How many of you again you went through and you feel whether you understood or any doubt? Only using LUB axiom. Start with the Cauchy sequence, and using that you defined a set as, that set as an upper bound, then use that upper bound, a non-empty subset of R as an upper bound mean it will have least upper bound. That least upper bound is our limit point of the given sequence. At least how many of you, some of you are able to follow, or you want me to recall again? Because that is very important. Cover told no mean you will have to come and give the proof. Anyone? Or at least orally. No. Some of you research scholars only will, yeah. No, at least any one of the MSc student, you are able to follow. Again I will recall quickly, I will not do everything. Using Cauchy sequence, what we got it? For epsilon, there exists a natural number such that, we will not write all the thing, such that x suffix n of epsilon minus epsilon less than nth term xn less than xn of epsilon plus epsilon for all n greater than or equal to, this is using Cauchy sequence. Then we selected the S equal to S of n of epsilon minus epsilon epsilon positive. For each epsilon, suppose epsilon equal to 1 by 10, then x n of 1 by 10 minus 1 by 10, this is only a notation. So like that we will get for every epsilon, but this is one element. X suffix n of epsilon is a one term of the sequence. N epsilon natural number, but is a real number where our sequence is in R. Epsilon is positive number, then this is also a real number. This is a non-empty subset of R. Then we proved that if we fix any other epsilon, 2 at a time we are fixing epsilon 1 positive. Then for this we have n of epsilon, for this we have n of epsilon 1. Okay, then this condition will be true when n is greater than or equal to n of epsilon, and here we write here epsilon 1, this will be true when n is greater than or equal to epsilon 1. At a time we want both should be, this should be true and this should be true. That's why n should be greater than or equal to both. Such natural number exist or not? N of epsilon over natural number, n of epsilon to another natural number, we can take the maximum sum, then we can find a natural number greater than, whenever n greater than or equal to n of epsilon 1 plus n of epsilon 2, then that n will be greater than or equal to n of epsilon 1. That means first inequality. N greater than or equal to n of epsilon 1 plus n of epsilon 2 implies n greater than or equal to n of epsilon 2. Then that second inequality will also true. That's why then we get this. Now this is true for every epsilon, this epsilon is fixed. Now for all epsilon, and this is fixed epsilon 1. This meaning is for every element from S, because an element from S means it is of the form x n of epsilon minus epsilon. Then that element is less than the fixed epsilon 1 plus epsilon 1. That's why this is an upper bound. And in fact for each epsilon, x n of epsilon plus epsilon is an upper bound for capital S. If we change epsilon 1 by 10, then x of n of 1 by 10 plus 1 by 10 is an upper bound, n equal to 1 by million, then x n of 1 by million plus 1 by million also upper bound. So every n of x suffix n of epsilon plus epsilon is an upper bound. That means that's why a sandwich, a sequence converges means what? It is between x n of epsilon minus epsilon and x n of epsilon plus epsilon. It is sandwich, neighborhood, it is in that x n of epsilon should be there, I mean x should be in that domain. So that's why this set S will have an x equal to least upper bound of S. Then we have seen that by LUB axiom it has an upper bound, hence least upper bound, that you call it x. Least upper bound means it is not, it is a real number. Then for every epsilon, now again start with for epsilon positive, x n of epsilon minus epsilon belongs to S, and x is an upper bound first, among the upper bound least. So first of it is an upper bound means less than or equal to x, and what is x n of same epsilon plus epsilon, this is upper bound for S, x is we have written x is least upper bound, x suffix n of epsilon plus epsilon is an